Today, I shall discuss about a universal Turing machine and recursive and recursively enumerable language. Consider the arguments against Turing thesis. A Turing machine is a special purpose computer. Once DEL is defined, the machine is restricted to carrying out one particular type of computation. Digital computers, on the other hand, are general purpose machines that can be programmed to do different jobs at different times. Consequently, Turing machines cannot be considered equivalent to general purpose computers. These objections can be overcome by designing a reprogrammable Turing machine called universal Turing machine. So, the universal Turing machine has two attributes. One is it is reprogrammable machine. Second, it simulates any other Turing machine. So, a universal Turing machine, MU, is an automaton that gives as input the description of any Turing machine M, and a string W can simulate the computation of N on W. To construct such an universal Turing machine MU, we first choose a standard way of describing the Turing machine. Universal Turing machine MU simulates any other Turing machine. Input of the universal Turing machine will be the description of the transition of M, the initial tape contents of M. So, for any input M and W, tape 1 will keep an encoded definition of M. Tape 2 will carry the tape contents of M. And tape 3, the internal states of M. MU looks first at the contents of tape 2 and tape 3 to determine the configuration of M. It then consults tape 1 to see what M would do in this configuration. Finally, tapes 2 and 3 will be modified to reflect the result of this move. So, we describe the Turing machine M as a string of symbols. We encode M as a string of symbols. Now, we can describe the Turing machine symbols A, B, C, D like this. After that, the encoding symbol will be A will be encoded by 1, B will be encoded by 1, 1, C will be encoded by 1, 1, 1, and D will be encoded by 1, 1, 1, 1, like this. The symbol 0 will be used as separator between the ones. Okay? So, the states will be encoded. States are Q1, Q2, Q3, Q4. States will be encoded like 1, 1, 1, 111, 4, 1 like this. That means Q1 will be encoded like 1 and the symbol 0 will be used as separator between the ones with the initial and final state and the blank defined by this convention. Any Turing machine can be described completely with delta only. So when we describe the head move encoding, the left head move we will denote is as 1 and the right head move will be denoted as 1, 1. So if we write the transition del Q1 comma A to, it will reach to the state Q2. After that, here I am writing here B and L. So after encoding, Q1 will be encoded as 1. This 0 is the separator. A will be encoded as 1 as the input symbol. And then Q2 by 1, 1. Similarly, B by 1, 1. 0 as separator and L by 1. Okay. So this can be appeared like this. encoding symbol will be like this for this particular transition. Now, if we consider the machine encoding for this transition, so what will be this? This is for A, this is for Q1, this is for A, then separated, this is for Q2, this is for B, this is for separated, this is for L. Now, this is the separator. This is for Q2, then separated, then for B, again separated for Q3 there is C1, then again one separator for C there is C1, then again separated, then 1 1 for right move. So this is how we can write the machine encoding. The transition how can be encoded. Step 1 contains of universal Turing machine encoding of the simulated machine M as a binary string of zeros and ones. A Turing machine is described with the binary string of zeros and ones. Therefore, the set of Turing machine forms a language. Each string of language is the binary encoding of the Turing machine. So the language of the Turing machine for machine 1, it can be 0101001001. Similarly, for machine 2, it can be 00100100141 like this. So these are the languages of the Turing machine. So we can say that from these observations, that every Turing machines can be represented by string of zeros and ones. So every Turing machine can be represented by string of 0 and 1s. This has an important implications. But before we explore these implications, we need to review some results of the set theory. Some sets are finite, but most of the interesting sets and languages are infinite. For infinite sets, we distinguish between the sets that are countable and the sets that are uncountable. A set is countable if its elements can be put into a one-to-one correspondence with the positive integers. By this, we mean that the elements of the set can be written in, say, some order. Say, x1, x2, x3, so that every element of the set have some finite index. For example, if you consider the set of all even integers, so it can be written as when you consider the set of even integer, it can be written as 0, 2, 4, 6 like this. So it has a correspondence like the 1 to it is the first number, then second, then third, then fourth like this. Since any positive integer 2n occurs in position n plus 1. See that the positive integers can 2n can occurs in position n plus 1. The set is countable. This should not be too surprising, but there are more complicated examples, some of which may seem counterintuitive. Take the set of all quotients of the form of P by Q, and P and Q are the positive integers. So how should we write the order to order this set to show that this is the countable? The set of rational number is countable, so we can write 1 by 2 as the rational number, then 3 by 4, then 7 by 8 like this. But we cannot write 1 by 1, 1 by 2, 1 by 3, 1 by 4. If we write it 1 by 1, 1 by 2, 1 by 3, then the correspondence, this is the first, this is second number, this is third. So in this case, it will never count the number with numerator 2. That means it will be numerator. So it will not count, never 2 by 3 will appear. So if never 2 by 3 will appear, this does not imply that the set is uncountable. In this case, there is a clever way of ordering the set to show that in fact it is countable. So how we will show that? If we depicted the number by the scheme, that means the 1 1, then 1 2, then 2 1, then 1 3, then 2 2, like this. So number will be represented like this. Okay. So here the element 2 by 3 occurs in the 8th place. And every element has some place in the sequence. The set is therefore countable. We see from this example that how we can see it is in 8th place. That means it will be count like this: 1 2 3 4 5 6 7 8. So 2 by 3 is in 8th place and every element has some place in sequence. The set is therefore countable. We see from this example that we can prove that a set is countable if we can produce a method by which its elements can be written in some sequence. We call such a method an enumeration procedure. Since an enumeration procedure is some kind of mechanical process, we can use a Turing machine model to define it formally. So, the set of rational numbers is countable by describing an enumeration procedure. Now, let S be a set of strings. An enumeration procedure for S is a Turing machine that generates all strings of S one by one. And each string is generated in finite time. Strings S1, S2, S3 belongs to S. So enumeration machine for S, when output on tape will be S1, S2, S3 in finite time T1, T2, T3. So the enumeration machines, this is the configuration for A at time 0. This is the Q0 state. Then at time 1, this is the QS states. In time 2, it is in this state, that is it will read, it will be in X2. In time 3, it will be in X3. So if for a set there is an enumeration procedure, then the set is countable. So what are the set? Here it will count x1, x2, x3 like this. The set of all string A, B, C plus, that means the positive closure of A, B, C is countable. We will describe an enumeration procedure for that. To show this, we will show it by an enumeration procedure. So now procedure produce the string in lexicographic order. A, 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 A. Starting string starting with B will never be produced. Now, the Breiter procedure is the proper order. Produce all strings of length 1, then to produce all strings of length 2, then to produce all strings of length 3, then to produce all string of length 4. So now the length 1, the string are ABC, then length 2, the string are A, B, AC. all the combinations of two string of length 2. Similarly, all the combinations of string of length 3. The set of all Turing machine is countable. So, how we can prove the theorem? The set of all Turing machines, although infinite, it is countable. We can encode each Turing machines using the binary string zeros and ones. With this encoding, we then construct the following enumeration procedure. What are the enumeration procedure? Generate the next string in 0 and 1 positive closure in proper order. That means the combinations of 0, 1. So find an enumeration procedure for the set of the Turing machine string. Check the generated string to see if it defines a Turing machine. If so, write it on the tape in the form of the definition, in the form of its definition. If not, then ignore the string. After that, return to step 1. That means this enumeration procedure is basically the generate the next binary string of zeros and ones in proper order. Check if the string describes a Turing machine. If yes, print the string on the output of tape. If no, then ignore the string. These are the basic methods to prove the theorem that the set of all Turing machines, although infinite, it is countable. Since every Turing machine has a finite description, any specific machine will eventually be generated by this process. The particular ordering of the Turing machines depend on the encoding we use. If we use a different encoding, we must expect a different ordering. This is of no consequence, however, and shows that the ordering itself is unimportant. What matters is the existence of some ordering. That means the existence of the ordering we have to consider. No need to consider that the order itself. So there should be a particular order. That's all. Now come to the uncountable set. We have defined the countable set, that theory. Now we will come to the uncountable set. First, we shall discuss that a language L is said to be recursively enumerable if there exists a Turing machine that accepts it. Similarly, we can say that a language L on sigma is said to be recursive if there exists a Turing machine M that accepts L and that holds on every W in sigma plus. In other words, a language is recursive if and only if there exists a membership algorithm for it. Now we shall discuss a set is countable if it is not, a set is uncountable if it is not countable. So we have to prove that. We can establish the existence of languages that are not recursively enumerable in a variety of ways. One of that way is that. The way is the set is uncountable if it is not countable. So this is the theorem. That means if A is be an infinite countable set, its power set 2 to the power s is not countable. So if S be the infinite countable set, the power set 2 to the power s is uncountable. Let S means the set of S1, S2, S3. These are the elements of S. Then any element T of 2 to the power s can be represented by a sequence of zeros and ones with a 1 in position I if and only if Si is in T. Okay, so for example, S2, S3, S6 can be represented by 0, 1, 1. That means the position which is given here, if we give here S1 and S3, it will be represented by S1 and S3. If we represent, it will be represented by 1, 0, 1. That means the position of S1 will be 1, the position of S3 will be 1, rest all will be 0. Similarly, if we represent S2, S3, S6, then the position of 2, 3 and 6 only will be 1, rest will be 0. That means the set can be defined as 0, 1, 1, 0, 0, 1, 0, 0 up to infinity. Similarly, in case of S5, S7, S9, S10, we can define the position of the particular cases will be 1, rest all will be 0 up to infinite. So clearly any element of 2 to the power s can be represented by such a sequence, and any such sequence represents a unique element of 2 to the power s. So we encode each element of the power set with a binary string of zeros and ones. Power set elements S1 will be encoded. That means here we can encode this as 1. Raised all at 0 up to infinite. S2, S3. These two are 1. Raised all at 0 up to infinite. S1, S3, S4. 1, 0, 1, 1. Up to this. Up to infinite, all elements are 0. So clearly any element of 2 to the power s can be represented by a sequence, and any such sequence represents a unique element of 2 to the power s. Suppose that the 2 to the power s were countable. So let us assume for contradiction that the power set is countable. Then its elements could be written in some order. If that is countable, so there should be some order. That means its elements should be written in some order, say T1, T2, T3, etc. And we could enter these into a table. Okay, so how we can enter the set into a table? Like this. So in case of T1, we can make the entry of 1, 0, 0, 0, 0 like this. In case of T2, 1, 1, then 000 like this. 000, then up to infinite. So this is basically the table which represents the elements. So 2 to the power s were countable, its element can be represented by some order. In this table, if you take the elements of the main diagonal, you will find the element 1, 1, 0, 0. So, and its complement in each entry will produce, if you complement this, that means 1 will be replaced by 0 and 0 will be replaced by 1. In this example, the elements are 1, 1, 0, 0. These diagonal elements are 1, 1, 0, 0. So, if we complement it diagonally, that means we will get 0, 0, 1, 1 as the result. Okay, so the new sequence represents some elements of 2 to the power s, say T1 for some I, but it cannot be T1 because it differs from T1 through S1. So when we got the T1, we basically got this, but when after complementing we get, that means we will get 0, 0, 1, 1. So for the same reason, it can be T2, T3 and other Ti. So it can be the any case of T. This contradiction creates a logical impasse that can be removed only by throwing out the assumption that 2 to the power is countable. So what is our assumption? That means that 2 to the power s or the power set is countable. That is wrong. So we can enumerate the elements of the power set. Then we can enumerate the elements of the power set. That means the contradiction creates it says that the assumption to the power s is countable, that is wrong. These kinds of argument, because it involves a manipulation of the diagonal elements of the table, that is called diagonalization. So it is called take the per set of the elements whose beats are the complements of the beat in the diagonal. Now the new element is 0, 0, 1, 1. It is the binary complement of diagonal. The new element must be some ti in of the power set. However, that's impossible. From the definition of ti, the ith bit of ti must be the complement of itself. So our assumption is contradicted. Since we have a contradiction, power set of 2 to the power s is uncountable. So we can show that in some sense that there are fewer Turing machine than there are languages. So that there must be some languages that are not recursively enumerable. Now, if the applications of the language, if we say the set of all strings A, B star, so we will get the infinite and countable language lambda A, B, like this. So here these are infinite and countable. So a language is a subset of S. So if the language is a subset of S, we can say the language is A, B, like this. So if we write the power set of S, that contains all the languages. So it will be L1, this may be L2, L3, L4. So it is uncountable. So the languages are countable, but the languages are uncountable, but the Turing machines are countable. So there are more languages than Turing machines. So there are fewer Turing machines than there are languages. So more languages, less Turing machines for that. So that there must be some languages that are not recursively enumerable. Okay, there are some languages that is not accepted by Turing machine. These languages cannot be described by algorithm. So languages that cannot be accepted by the Turing machine, that is, suppose that is LK. So these are the languages accepted by the Turing machine. Now we will define also, we will prove one theorem. That means for any non-empty sigma, there exist languages that are not recursively enumerable. So as I have described, you have to show like this. First, you have to decide that a language, first you have to assume that a language is a subset of sigma star. And every such subset is a language. Therefore, the set of all languages is exactly 2 to the power sigma star. Since sigma star is infinite, the theorem says that the set of all languages on sigma is not countable, but the set of all Turing machines can be enumerated. So the set of all recursively enumerable language is countable. So this implies that there must be some languages on sigma that are not recursively enumerable. So every language that can be described in a direct algorithmic fashion can be accepted by a Turing machine, and hence recursively enumerable. The description of a language that is not recursively enumerable must be indirect. Nevertheless, it is possible. The argument involves variations on the diagonalization theme. There exists a recursive enumerable languages whose complement is not recursively enumerable. Then another theorem we must know, that a language that is recursive enumerable but that is recursively enumerable but not recursive. Under this, we have to prove on theorem if a language L and its complement L complement are both recursively enumerable, then both languages are recursive. If L is recursive, then L complement is also recursive, and consequently, both are recursively enumerable. So today I will complete up to this recursive and recursively enumerable language. Thank you.
রেকর্ডিং হলো তো নাকি?